So feel free to close those MacBooks. And let's get going. So here we go. Let's make sure you have out that packet that we dealt with before. We're going to look at some new formulas. We're going to play around with this pendulum here. And then we're going to talk about damped oscillations. We got all kinds of good stuff going on here. So let's just go ahead and make some observations about the pendulum so we can see what happens. All right. Right now I have no friction going on. That's going to happen at the very end. I have the gravity, which I can go from none to lots. Let's see what happens when we go more towards the lots. What's happening to that pendulum?
It's faster.
Yeah, it's going faster. So we can talk about the frequency
Has increased.
and the gravitational pull went up, and so the frequency also went up, right? It's going because higher frequency. So what about the period when the gravitational?
It's shorter.
Yeah, it's a shorter period, so it went down. That looks like a what type of relationship? Inverse relationship. Okay. Like if I go all the way down to none, it's gonna.
Like a circle.
Yep. We'll go to some. Okay. All right. Let's go ahead and change the length. So, as the length decreased, what happened to the frequency? Yeah, it increased. The frequency it's going back and forth faster. So as the length decreased, so a shorter length, the time period, the time that it goes from back and forth, yeah, it also decreased. So what we have is the time period we're not sure exact relationship, so it's somehow related to the length in the numerator and the g in the denominator. All right, because the g is an inverse relationship with the time period, and the length, it's a proportional relationship. Just to make sure, if we increase this length, yeah, then the time period increases as well. Let's see what happens with the mass. What's going on with that?
It doesn't depend on
Yeah, it doesn't really look like it depends on the mass very much, does it? Yeah, in fact, it doesn't at all. At least not for small angles. Can we? Oh, so we could have done that.
That's cool.
All right. We could add another one. But yeah, I like this one right there. Obviously, if we add friction, you can see it gets really small really quickly. Never hits that previous spot again. Okay. Let's go to this energy. What is this going to show us? All right, so after at the top, we've got what type of energy?
Potential.
All potential. And then all kinetic. All potential. Look at that total energy. What do you notice about the total energy?
Never change.
Never changes. It's a constant sum of the kinetic and the potential. In fact, if you, we have a special name. I don't know if the book talked about it, but I'll tell you now. Total energy, kinetic plus potential. There's a special name for it. Anybody catch it in the readings? Mechanical energy. The total mechanical energy, TME, is that, are we recording?
Yes, sir.
Okay, great. Thought there we weren't recording. Okay, so let's go ahead and add friction here to the mix. And you'll start to see that thermal swinging up here. We'll speed it up here. You can see thermal is becoming an increasing part of that system. And as a result, there's less for the kinetic and the potential to play with. And so eventually here, we'll see it come to a complete stop if I can put up on the lots. So just sort of getting used to that idea even more. Okay. There is a formula for the time period of a pendulum, and that is equal to 2 pi times the square root of L over G. So they're not. It's not completely a linear relationship. It's a square root relationship. And then just like we saw, the frequency of a pendulum is going to be the inverse of that. So 1 over 2 pi square root and the reciprocal of this, G over L. And that matches what we saw. Sorry, I probably should have put this one down here, but you get the idea. That's on your AP formula chart, so make sure you find your AP chart, put a star next to it. We'll stop it so that it doesn't continue to go on forever. In the book, they went through that whole process. So frequency, 1 over 2 pi G over L, and time period, 2 pi L over G. Very similar to the spring, but we can see once again the things that make the difference in the time period, length of the gravitational pull. Stuff that doesn't make a difference. What are the things that don't make a difference in the pendulum period? Mass, also. Oh, it's over there. Yeah, the initial amplitude does not make a difference in that time period. Okay? So let's see if we can very quickly answer these questions. At which point or points is the speed the highest? When is this thing going to be going the fastest, folks?
C.
At C, that's right, when it passes through equilibrium. When is the acceleration the greatest? Now remember, acceleration is the greatest when the force is the greatest. What do y'all think? A and E, both at the end points. When is the restoring force the greatest? Yep. Like I think also C, right there at the middle, because it's pulling straight up. A, E, and C. Oh, no, you're right, A and E. Okay. Oh, now this is weird because they've got it going in different places. Okay, so this one's not. All right. So we've got equilibrium here at B and D. C, it's, I'm assuming, well, we don't know which way it's moving on that one. Maybe. All right. When is the acceleration 0?
B and D.
B and D, right, as it's passing through that equilibrium point.
Why is that?
Why is the acceleration? Because there's no net force on it. If we were to look at all the forces acting on it right here, what are the forces that are acting on it?
Just the weight
Weight?
and tension.
Yep.
There's no horizontal force.
There's no horizontal component of either one of those. Now, you're like, wait a second, there's tension and weight acting on it at all times, and you're right. For instance, consider the moment right there. Let's draw the free body diagram for this point. Weight going down, no different, but also tension is at an angle. So that has an X component and a Y component.
So the acceleration is the greatest there.
Yes.
The longest X component.
And then the net acceleration is this part here, because the vertical part is canceled out by the vertical up on the tension is canceled out by the weight going down. What is not counteracted is the weight force, or the horizontal component of the tension. So that's Tx, and that is what this part right here is the linear restoring force, because that's what is pulling it back towards the center, and it's biggest right there in the end and at the other end over here. And I don't know why I said it was on our previous slide that it was at the equilibrium, because it wouldn't. There's no restoring force at equilibrium. There's a restoring force if you're away from equilibrium. When is the kinetic energy at a maximum? B and D again. Because kinetic energy, remember, 1/2 mv squared. You'll need to know that formula as well as the other mg delta y formula when you take your quiz. Previously scheduled for today, now pushed till Monday. When is the potential energy at a maximum? This isn't too bad. A. Yeah, the other points, we're not indicating that it's at the highest point. So VD,
Oh, they're saying C and E are equal, but A
There's-
looks more sensitive.
yeah, they're saying that C and E are at the high. Nah, I don't like that answer.
Can I tell you that on a quiz, but I don't like it?
You can tell it to me, but it is not going to hopefully make points here. All right, so this one, it says that the got a ball on a massless rigid rod oscillates a simple pendulum for a period of 2 seconds. If the ball is replaced with another ball having twice the mass, the period will be
2 seconds.
Aha, trick question. Why is it 2, Ivan?
Because the period does not depend on the mass of the object.
Great answer. On planet X, a ball on a massless rigid rod oscillates the simple pendulum for a period of 2 seconds. If the pendulum is taken to the moon of planet X, where the free fall acceleration g is half as big, how will that affect the period? Alright? This is how I would set up this problem. I would write it, this is on planet X, and this over here is for the moon. You can write that formula, 2 pi square root L over G, and that's equal to 2. The period on the moon, 2 pi is the same. The length of the pendulum is the same. But what's up with the gravitational pull?
Is 2 times.
It's
Oh no, half.
It's half of the original. So I'm gonna put 1/2 times G. So what I want to do is I want to just algebraically manipulate this so that it resembles the first one, and then I can just substitute it for 2. So I've got 2 pi, and then I'm going to rewrite this as the square root of L over G times the square root of 1 over 1/2. Y'all remember your property of radicals that you can split apart square roots? So this from our first equation we saw was 2. What's 1 over, I mean, good grief, that's a crazy lot of stuff. We could rewrite that as the numerator times the reciprocal of the denominator, so 1 times 2 over 1, so it's just root 2. So 2 times root 2.
Oh,
So-
you brought the answer.
Yeah, I replaced 2 pi square root of L over G with 2, and I'm rewriting this 1 over 1/2 as 1 times 2 over 1. So this is the square root of 2. So this is 2 times root 2, which is 2.8. As far as I know, this is probably one of the fastest ways you can do that, unless you know automatically that because it's in reciprocal and square root of 2. Anyway, this is a great way to set these problems up. Write the original equation, then write the new one with whatever you have changed, and then see if somehow you can pull that multiplier out off to the side, and then rewrite the original thing with the actual number value again. You can see what happens. All right, I'm willing to. I think we're pretty good on this. We'll do one. We'll do this one problem. So here you go. Last one on that handout that you have. Grandfather clock is designed so that one swing of the pendulum in either direction takes 1 second. Okay, that's pretty cool. So it goes tick, tock, tick, tock. Okay. What is the length of the pendulum? All right, well that makes sense because we know that the period does depend on the length. So that's, I can see why they call it that. So we'll put period of a pendulum is 2 pi times the square root of L over G. So if one swing in one direction is 1 second, what is the period? 2 seconds, that's right. So 2 equals 2 pi square root L over G. They're just wanting us to solve for L. So we have 2 over 2 pi. Then we'll square root both, or sorry, we'll square both sides. And then multiply both sides by G. And that'll give us L. So while I take attendance, go ahead and take care of that. 2 divided by 2 pi. Now you want to make sure that's in parentheses, otherwise you're getting weird answers. Square it, multiply it by G. Tell me what you get here in 1 minute. What do y'all get? 0.99? 6 or 3 or what was it?
2 or 3
Okay, so 0.993. What are the units on that?
meters.
Meters. Have y'all ever seen a grandfather clock? What does it look like? How big? That would be a clock, but it's not an official grandfather clock. Keep going. I mean, it's at least, it's almost an entire meter. It's 0.993 meters. So that would be from there all the way to here. So grandfather clock is, normally the arm is that long. Because it just, rotates about tick, tock, tick, tock, tick. Yeah, it's pretty good actually, right? I'm just trying to let it swing here. 1, 2, 2. Okay? Now, let me bring this over here. And we're going to talk about adding energy to the system. Driven and damped oscillations. All right. So what we're going to do here in a minute, after I hand this out, we're going to think about what would happen if periodically I add energy to the system. What are y'all seeing? What's happening as I'm adding energy to the system?
The period changes in the speed and the
Maybe, okay, alright. Alright, so that's what we're talking about. One for you, there's one for you. Alright, oh, we can't talk about damped oscillations yet. We gotta talk about our driven. That's the fun stuff. We'll talk about damped oscillations All right, so an oscillation that slows down, comes to a stop, is called a damped oscillation. Basically, we've been living sort of like in a perfect world up until now. We've been saying ignore friction, it's not a thing, right? Okay, but in the real world, you have energy loss due to air resistance, due to the rotational frictional effects there at the hinge, or where the rope is meeting the pivot point, or the frictional effects of the spring actually stretching and compressing. There's thermal energy there. So as an oscillation decays, the rate of decay decreases, and the difference between each one of those peaks is less. Or with the spring, you saw it would go less and less each time. So you end up with this thing called a damped cosine wave, or a damped sine wave. Have we talked about this in pre-cal yet? Did you have to graph these? Okay.
Last semester.
Was it last semester?
Mm-hmm.
Okay, cool. With the sines and cosines? Okay, yeah. So what it was that it was an exponential decay, which we talked about recently in pre-cal, okay? Both from the positive and the negative, and your cosine is bounded by that, okay? So normally your sine or your cosine is bounded by just whatever numbers at the front. Like, it's always going to have an amplitude of 1, and so it's going to be between positive and negative 1. But in this case, it's being bounded by that exponential decay, so it's only going to go up to the highest value of that exponential decay, or down. And so it's really kind of interesting, these things that seem to have absolutely no real connection, like sines and cosines and exponential, right? They have an absolute connection when it comes to oscillating systems, okay? And the general formula we have here for this exponential curve, you may recognize that, is a e to the negative t over tau. So you've got your a, which is your maximum value right up there, your y-intercept, and then e, which we talked about in pre-cal actually today, the Euler's number, and then this is negative with the exponent because it's going to bring it down there. T over tau, tau is used to talk about the time of displacement till it degenerates to a certain point. And there it is, Euler's number, 2.718. It's based the natural logarithm. Anyway, so t is called the time constant, and like I said, it's the time that it takes to decay a certain amount. Specifically, 37% of its initial value. All right. So mathematically, this is kind of interesting. The oscillation never ceases. In fact, if we look over here, even this guy is still kind of going for a little bit. All right. However, the amplitude will be so small that it's undetectable. In practical terms, tau is the lifetime of the oscillation. It tells you how long it takes to decay. So if you have a very small tau, then compared to your time period, then it may go for a really long time. Have you all been to one of those museums or anything like that, or like a science museum or a children's museum where they have a giant pendulum at the front and it's going back and forth and knocking over like dominoes and things like that? It changes over the course of the day, showing the Coriolis effect. Have you ever seen that? It's a giant. Oh man, it's awesome. Oh, it's one of the greatest things. It's this giant ball in the middle of like the room, and there's all these like dominoes and stuff like that. And because of the spin of the Earth, and then it actually it knocks down different dominoes at different times of the day. Man, all these great experiences we need to have here. All right, so otherwise you can have quick oscillations. Okay, so there you go. There's damped oscillations. It's pretty much everything you need to know about that. But this is the real fun part. Driven oscillations, okay? Because you get all kinds of really cool stuff with this. A driven oscillation is when you've got something that's oscillating that is experiencing or subject to a periodic external force, such as my hand pushing this pendulum. Gracie, can you make sure we get the camera on this? All right. So I'm going to be adding a force to it, but I'm adding a force periodically. Maybe say once every second. So 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi. What the heck is happening to this?
It's not getting to a finish. It's
Okay, yeah, it's not going to get finished. But what else is happening? I mean, it's not going to come all the way up here yet because I'm hitting it at exactly it's over here. What else? How would you describe what's happening to that pendulum? Is it decaying?
It's increasing.
getting bigger.
What is increasing?
The
The kinetic energy.
Okay, there's more kinetic energy, absolutely. What else is increasing?
the amplitude.
The period.
Okay, amplitude is increasing. You might think that the period is increasing. However, what does the period depend on?
The length and gravity.
The length of gravity. Am I changing the length at all?
No.
Am I changing gravity?
No.
No. Now,
It's just moving faster.
it is moving faster because it's got to cover the distance from here all the way to here in 2 seconds.
Mhm.
Okay? Whereas right here, it's got to go from here to here in 2 seconds. So it's going, the actual velocity of the ball is going faster, but its frequency is the same, its time period is the same. It's just like I said, it's the difference between going between here and here in 2 seconds and from here and here in 2 seconds. Okay? So the frequency is the same. The time period is the same. What's changing is what we call the amplitude, or you could say the amplitude response. Okay? So there is an amplitude response when I'm hitting it once every second. 3 Mississippi, 4 Mississippi. Well, I kind of slowed down a little bit that time. Okay?
Mhm.
Now, it just so happens that this is about 1 meter long. It's almost like a grandfather clock right there. So that's, remember, our grandfather clock had a 2-second period. Okay, so I'm hitting it at just the right time. What if I were to hit this, give it an amplitude, I don't know, maybe every 1 second? Am I hitting it every 1 second?
Yes.
I am hitting it every 1 second. So I'm gonna try to hit it, I'm gonna hit it faster. I'm gonna have to be super quick here, right here. So I'm trying to hit it every half second, okay? 1 and 2 and 3 and 4 and
Isn't that still
5
every 1 second?
and, okay, I don't know. Should I go every 5 seconds?
Yeah.
Or every 3 seconds? Okay. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10 Mississippi, 11 Mississippi, 12 Mississippi, 13 Mississippi, 14 Mississippi, 15 Mississippi. Okay. It's not as easy here, but can you see what's going on? I know it is changing.
I don't know.
I'm not sure if this is exactly
Increasing, then decreasing, then increasing again.
Okay, yeah, it's increasing. Well, yeah, I'm trying to get that point across, that it's not like I'm hitting it at the exact right moment
Mm-hmm.
so that it builds upon itself. Okay? Instead, when I'm hitting it and I'm sort of like not in sync with the natural frequency of the pendulum, then it's like we're fighting each other. Okay? I think of it, it's like if I'm pushing my son on the swing, I'm going to push him every time, he's right here at approximately the same rate, But if I start pushing him here, and then here, and then here, and then here, and then right there, you see what I'm saying? Like, if I'm pushing him at what we'd say not the right frequency, okay, then he's gonna just kind of go back and forth and stuff like that, and we're not going to get a bigger and bigger and bigger amplitude response. Does that make sense? So what we can do is we can talk about the natural frequency of this system. The natural frequency is 1 over 2 pi times g over L. Okay? But we can also talk then about the frequency that I am applying energy. Okay? And maybe and the truth is if the frequency that I'm applying energy is the same or close to the natural frequency, then you get some really big amplitude response. Okay? So that's the first idea. when the driven frequency, we'll say the frequency that is driven is near the natural frequency, then you get a very large amplitude response. Otherwise, my external force is going to end up fighting it, and it actually, you get almost no amplitude response. Does that make sense?
Mm-hmm.
Okay. So it's going to be in sync with the pendulum. All right. So Fx, okay, that's what I said. The driving frequency. I put frequency driven. I don't know what the heck I'm thinking. I just look over there. Okay. Fxt. So the driving frequency is a periodic external force of frequency. It is independent of the natural frequency. It's totally dependent on what my mind is making of it. Natural frequency is the frequency that the system, if it's displaced from equilibrium and released. Think of when they had their backpack over here hanging on the door and it was bouncing up and down, it had a natural frequency, okay? We could go over there and start pulling it down every couple of seconds or whatever, and if we got it just at the right time, at the right frequency, then we could make that thing go and bounce up and further, you know what I mean? But if we don't put it, don't start pulling it or pushing it up at exactly that same frequency, then we're going to end up fighting it, and it'll end up kind of just sort of staying around there, okay? So this is a graph showing that amplitude response for different frequencies, okay? So here, the natural frequency is 2 hertz, okay? Like how fast that pendulum would naturally swing back and forth. If I drive it at 1 hertz, I'm going to be fighting it more than anything else, and so the amplitude reaction is not going to be very high. But if I start pushing it around 2 hertz, so even if I'm at like 1.9 or 1.8 or 2.1 or 2.2, if I'm driving it, having an external force near that, then I'm going to get a very large amplitude response, which is what we saw when this thing started swinging back and forth here, or when my son ends up going over the bar and becomes Inside Out Boy. So that's a really old pop culture reference. I'll check you get that one. So anyway, that's what this graph here. It's a great graph, and you can see how it starts to peak here, where when I put different external frequencies, I'm going to get a larger amplitude response. And different systems have a different response graph, okay? So there's some graphs, there's some systems, maybe like the spring over there, if we had the backpack and the spring, maybe that graph might look something, oh, it's not, oh, okay. It might look like that, where if you get it right on the nose at 2 hertz, boom, it's gonna go crazy up and down. It's gonna have a very large amplitude response. But if you're, if you're off by just a little bit, then you're gonna be fighting it more. It just depends on the system, what this graph looks like, and the actual shape. So this natural frequency right here is also called the resonance frequency, okay? It's the frequency that it normally wants to resonate at, okay? And we're going to be talking about that resonant frequency in later chapters, especially when we talk about music and instruments. And there's some really neat stuff, because you want your instrument to resonate at the natural frequency, and you can change the natural frequency some different ways. So here you have different systems. Like I said, those different graphs. This one right here is a system with significant damping that has a much smaller response. So if you've got a lot of friction, then even if you're pushing it at the resonant frequency, at the natural frequency, then you're not going to get a big response. But if it's very lightly damped, means not a lot of friction, then you're going to get a very tall and very narrow response curve, and you can get some crazy amplitude reactions. This one, actually, I'd say this one's pretty lightly damped. So I'm not putting a whole lot more energy in it, and it is really going up higher and higher. This counselor's class probably wonder what the heck is going on. So resonance in the system means that certain frequencies produce a large response and others do not. This is one of the ways that kind of your ear works, is that there are some frequencies that you can pick up on better than others. And depending on where these different sensors are, these little membranes and stuff, and they vibrate. It depends on the distance that they are, just like it depends on the distance there. So there's some neat stuff there. You get the length along there corresponds. You have different frequency responses, and then that allows you to hear the sound better. This will make more sense after we talk about sound, so we're going to kind of hold off on that. Hey, wait a second. We're not finished. What? Well, that's not. I thought we have one more thing. I want to show you what happens if you are an engineer and maybe you're not aware of these principles. Okay? That you have things like a natural frequency. Okay? Because anything that you might build, like maybe a building or a bridge, okay? If you think of a bridge, okay, that is between two things, okay? And if it's kind of hanging there, it's going to have, it's kind of like a pendulum, it's going to have a natural frequency that it goes back and forth on, okay? So, see if you can, all right? So if I'm going to sort of like let this bridge go back and forth, I've got it extremely loose here so we can see. Now imagine if some giant was to come by and periodically push this this bridge at the same resonant frequency or near it, okay? What would happen to this bridge? It pushes it near that resonant frequency. Eventually, it's going to fall apart, okay? Now, what I'm going to show you is a video, but it's not of a giant who pushes on a bridge. And it's not an earthquake, though they have to take that into consideration as well. But something, what's that?
Just wind?
Just wind. All right? There was a special place, I can't remember which state it was in, anyway, and the wind would come down, and it would come in bursts and gusts, okay? And it just so happened that the wind bursts and the wind gusts were very close to the natural frequency of the bridge based on its length, okay? So, guess what happened? The wind started blowing, and it just was kind of windy blowing, and it started to move the bridge back and forth a little bit, okay? And that wasn't too big of a deal, except that the wind would kept blowing at that near that natural frequency. And so it started to have a larger and larger response, okay? Was there friction? Yeah, but the wind would just keep blowing, adding more energy to the system. And it started going back and forth, and eventually the bridge fell down.
Fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the feather span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick.
It's not so much that the wind is strong. There's been winds a lot lot
Back
stronger
out of the
than that.
danger zone,
It
all
just
three
builds.
inspectors
It just-
have
it
driven
just- it just
safely
kept
as the
building
bridge
on the
gyrates
system,
like
yeah.
a nightmare high above the river.
So it all just
Twisting, turning, curling.
Yeah, it was the fact that it was at
The
that natural
locomotive reports
frequency.
goes after the car. He has but a few minutes in which to save himself.
This guy goes, it's a
Face
professor
to
actually.
face with fate. His destiny
get out of his
hangs in the
car.
balance.
There was a dog, I think, in the car.
Will he heed the last warning or perish with the doomed structure? But he saved himself
Oh,
by
it's casual.
seconds.
He's just walking.
Yeah, he's just like, I got it.
It's not the whole bridge is just shaking.
Unfortunately, they did not have the camera on it at the exact moment that it fell.
No structure of steel
Is
and
that it
concrete
falling?
can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes!
Oh!
They got close.
It's still just.
Oh yeah, it's still good.
Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders. Others differ. But whatever the reason, Tacoma will rebuild. This time a bridge that will not provide a super thrill in the news.
I get like the feelings behind making it move. It just crazy me that material, like
Could that happen?
the stone can do that.
Could that happen too? I can't. What's the big bridge that's red?
Uh,
You know what I'm talking
Golden
about?
State
the same-
Bridge.
The golden.
Yeah, the
Golden
one
Gate
Bridge.
Bridge.
Yeah.
Gate Bridge.
Could that happen to that?
It could if the you know, the wind would blow it exactly that, you know, the resonant frequency, but they, you know, have learned since the Tacoma Bridge.
Yeah, don't they put that into the structure that it can take so much before it actually starts?
They can, and they also can. They can adjust it, and but I mean, everything's gonna have a natural frequency, but they can just make its length such that the natural frequency is nowhere near what
wind's
the the wind in that area is going to, you know, regularly
That's crazy.
give. So, anyways, now you understand how that works. Anyway, and we'll this principle we will see over and over again when we actually get to sound, okay? Because that's how you get amplification and something called a standing wave and some really cool stuff. Anyway, all right. So this now completes chapter 14. We'll take the quiz on energy and work, more energy than work, I guess, on Monday, and we'll start chapter 15 on Tuesday.